to the first part, the question, can you just rephrase that question? This reiterate.
So essentially,
Oh, sorry. Yeah. Oh, so the spin accumulation,
explanation,
if it's collinear to the magnetization, you do not expect it to exert a torque.
yeah, it should not change magnetization dynamics. It's kind of you lose angular
So
momentum
you
along the
can
magnetization.
argue, say there's say two. I could think of like say two mechanisms, for example, some magnetic mechanism where you have some third intermediary that you talk to some magnetic cloud. Or if you think of it in an example for like in a SD-like picture, which is the preferred picture I like to think about, is that these anomalous Hall and planar Hall effects give you a tuning of the S-like electrons, which then can couple to the D-like electrons, and if they have different scattering rates, they can exert torques.
But it's just conservation of angular momentum. If you lose angular momentum along magnetization, how can you have a torque?
Yeah, so how do you, for example, this would be some like argument. So the spin Hall torque, for example, should not work. If it has a M cross M cross P, why is it strongest with P? And you invoke some thermal fluctuation or something like that.
No, it has this normal spin orbit torque has a preferred direction, but in your explanation, the only direction you have is the direction defined by the magnetization.
No, and the broken inversion symmetry and the current direction are important too.
Yeah, but in your explanation, I did not see any other vectors. You just said that you lose angular momentum along magnetization.
Oh, okay. Yeah. So the full form will be like something like this.
Yeah, no. So if you look at your ferromagnet, it loses angular momentum, right? And that causes the torque. But if angular momentum has the same polarization as magnetization, how can it induce any magnetization dynamics? So what I'm saying that your explanation probably needs to be slightly updated.
Okay.
All right. Thank you for nice talk.
Okay, we'll go to Mahendra. Please go ahead and ask your question.
Hi, very good presentation, Eric. So I have a question related to the anisotropy, if there is any present. So right now you have a current flow along X. So if you make devices current flowing along Y or along 45 degree, if you see any difference in your results.
Well, yeah, so it's gonna be the specific MY is a consequence of our current density or our E field is defined to be in the X direction. If you have some different geometry, it's actually going to follow something that's shown here with this JFM. It just happens that our JFM is in the X direction in this specific geometry.
Now I see that, but what I mean is like you have grown in certain substrate, right? So if we make device just the same device, but you rotate by 90 degree. Now your current flow is along y-axis, right? The same device, but you are making, yeah.
I don't see how that's not just a rotation of coordinate system. The effect doesn't depend on the coordinate system that you define. Maybe I'm missing something that you're.
From the from the material perspective, so you flow current along a-axis versus b-axis, if you see any difference. So that's my question.
Oh, if like in something that has a magnetic anisotropy built in, I'm not exactly understanding the question. So if you took the same nanowire and you just rotated the axes by 90 degrees, there's no difference. But if you are you talking like you have some intrinsic uniaxial anisotropy or something like this? Or
Since it's related with the magnetization, right? So maybe there is some anisotropy present. Maybe just I'm not
I'm
sure.
sorry, I'm
Just
not quite getting the question. But so this form you could include into the LLG,
Mhm.
and your anisotropies would be included in this H effective. Does that help answer?
Yeah, it seems it will not make. Yeah, I think we can get. Yeah, that's possible. Yeah.
If you do nothing but just rotate the coordinate system, that's not going to change the physics.
Okay.
Mahendra, are you referring to if the sample has certain, it's a single crystal, so it has the crystal anisotropy, depending on whether C-axis is aligned?
Somewhat close. Yeah.
So if you want to introduce extra anisotropy to this system, is that?
Like for example, let's think of MOT2 results, right? So there is A axis versus B axis. There is a low crystal symmetry. Then in A, I don't remember exactly, but in one axis you get unconventional spin, but another axis you will not get unconventional spins. So if anything similar happens here, so that's my question.
Do you mind following up with me?
Okay,
Sorry.
no worries. Yeah, we can like start offline. Yeah, so no
Okay.
worries. Yeah.
Great. Do we have excuse me, other question from the audience? Let me check on YouTube. But I actually want to ask a quick question. Regarding the angle dependence, now it seems that the formula suggests that it should be sine theta cosine theta squared. That would suggest in this graph, if the magnetization is aligned along the y direction, then the AHT, anomalous Hall torque, is strictly zero, right?
Yes.
But why should that be? Because this is a geometry where you would expect the anomalous
sorry.
spin anomalous Hall to take part.
Let me clarify. The anti-damping response, the change in the damping is zero. The total torque is not zero. So the dissipative component of the torque, or the divergence of the torque, is zero along the y-axis, but the net torque is not zero.
So if the magnetization is along y direction, and I'm just thinking about anomalous Hall effect, you are generating a perpendicularly flowing spin current with spin polarization along the y direction. So that's exactly the same as what a spin Hall effect will give rise to. And this is going to leak out of the ferromagnet, be absorbed by the non-magnetic materials, and it's still going to cause a backflow in a subject that. But why wouldn't this configuration generate an anti-damping torque, because the spin is either parallel or anti-parallel with the magnetization?
Yeah, so I'll show you some. Okay, yeah. So if you go to this paper that shows the first theory for these self-induced spin orbit torques in ferromagnets, specifically with relating to anomalous Hall and planar Hall effects, just in their notation. So this is your LLG. The torques we're looking at have a form like this, where the spin accumulation has a form like this, where this theta H is anomalous Hall like, and this rho MR are planar Hall like.
Okay.
What you find is if you have a torque, if you add this torque, say just one of these terms, to this LLG, you then linearize your LLG and you add a drive that's, say, B e to the negative I omega t, where this B is your, say, FMR drive. This is small. You assume damping small. You linearize, you solve the LOG, you linearize, and you solve for the transverse microwave susceptibility given by here. What you find is that these torques lead to a modification to the transverse susceptibility that has this term that goes as the spin accumulated density and the projection in the z direction squared. This
Okay.
term here is what turns the torque off in the y-axis.
Because z dot n is equal to 0.
Yes.
Okay. All right. Okay. I'll have to look into this.
Yeah.
More details. Yeah. Thank you very much.
Mhm.
Okay. Do we have any other question? If not, we'll turn off the live